All right, here we go. Hello, everyone, and welcome to my talk, which is entitled, What is Probability for the PyMCon 2020? And it is great to be here virtually, and I look forward to seeing you all virtually, but live on October 31st. So first of all, I want to introduce myself a little bit. My name is Max Sklar. I am currently a labs engineer at Foursquare. I'm actually a longtime engineer at Foursquare, which means that I work on experimental consumer products. So the one that I work on now is called MarsBot Audio, and it should be out in the App Store by the time this goes out. But if not, you can ask me about that. We're not going to talk about too much about that today, but I do have a lot of experience as a machine learning engineer at Foursquare, which I did for many, many years. And I was able to kind of develop a toolkit of Bayesian methods when I was there. So we'll talk about that a little bit. And also, I have a weekly podcast that I do called The Local Maximum, and you can get information on there at localmaxradio.com. I'll be talking a lot about the podcast, but there's a good reason for that, so hang tight. So first of all, you might notice something a little bit different about this video. First of all, it's, I don't have slides, which is a little different. It's something I'm trying that's a little different. I think I can put some funny pictures up for you. I can spend hours looking for pictures, but I'm kind of, with the podcast, I'm kind of growing accustomed to talking without slides for the podcast. So let's see if this works. Now, you might be like, well, I want to go back to the slides. All of my notes for this, including the links with my notes, I have about 3 pages of notes, and they'll all be available to you with links after or before the talk. So since we don't have slides, I'm going to assume that you know a few things. I think if I had slides, first of all, I would put up Bayes' rule, but I'm going to assume that you all know Bayes' rule. Probability of a hypothesis given the data is equal to the probability of the data given the hypothesis times the prior probability of the hypothesis over the probability of the data. Or the way that I like to put it is posterior is proportional to likelihood times prior. So that's kind of a basic thing. I'm going to assume you have that. I assume you have kind of the basics of how Bayesian inference works. And if not, it might be helpful to pull that up and familiarize yourself with it a little bit. But I think most of the people in this conference are solid on that. So that's kind of where I'm going to go from a starting point. And I'm also going to assume that you have dived in some real problems before involving Bayesian inference. And so I'm going to prepare you for how to do that in the future, or I'm hoping that you think about the problems that you solved in the past, and you kind of think, hey, these questions have come up, which is very surprising. So the question that I want to start with today is, what is probability? And that is a really interesting philosophical question, and it might be, there might be a tendency for practitioners to say, well, I don't really care about probability. I don't care about epistemology. I just want to solve problems for my client or whatever it is. And sometimes that works, but actually, sometimes you really have to dive into some of these philosophical questions, because it does have implications for the practice of Bayesian inference. Because, well, first of all, after all, a lot of us are often tasked with justifying Bayesian methods. Not every place and not every client that you're going to deal with are committed Bayesians like us. I assume most of the people who are listening today are committed Bayesians, but the average person is not well versed in probability. The average person in sales, or the average person in management, sometimes they're very smart people, hopefully, but they're not always well versed in probability itself. Not even putting aside, I don't even have time to go into all the different schools of thought into probability. So it's very important that we often be sharp on these things, so we know where different people are coming from. And if somebody comes at us from a different angle, we should be able to understand where they're coming from as well. So that's pretty important. This talk is going to be informative for those of you who are kind of new to Bayesian inference, but even if you're experienced, I hope you find one or two, or maybe a lot of new pieces of information or points of view that you can carry around in your toolkit. Looking at probability is kind of the essence of looking at all of the problems that we solve in our work and in our research. So early this year on the podcast, on the Local Maximum, I kind of decided to explore this further with a series of episodes. And I'll be forwarding the episodes for you to check out. And I know you might think, hey, why are you pushing your podcast on us the whole time? But look, I already did the work in presenting some of these ideas and talking to some experts and making show notes available. So I do want to tell you about all the work that I've already done, several hours of content, and it's really packed with information to teach you about different angles here, because I can't do it all today. So I've done the work to make it available to you for free. So localmaxradio.com is where the podcast lives, and I'm going to be pointing out specific episodes if you want to dive into some of these issues more that we're going to cover a little bit more in depth. So first of all, a couple of practical examples that really made a difference for me when understanding probability. The first is from a problem that I dealt with at Foursquare several years ago, which is the problem of marketing attribution. Very big business for Foursquare, very big business in general. And that is kind of the task of trying to figure out whether ads work or not. And there's a whole lot that I can say about causality theory, which is a whole other issue that I had to dive in for that. But also it was just a matter of how we presented our results to the client. So for example, the client wanted to know, did my ad work or not? And really, when we dove into that problem and we tried to figure out how do we answer this, we realized that the right way to do it was kind of a Bayesian inference. And the thing that popped out at the end was something called lift. It was like, what is the average likelihood that someone would visit your place, given that they saw the ad, over what would have happened if they hadn't seen the ad? Very difficult thing to compute. But even once you can compute an estimate, you don't want to give an exact number there. What you want to do is you want to give an estimate for, hey, I think the lift was 10%, but I have, say, a Bayesian credible interval that I think it was maybe between 5% or 15%. Or maybe, I think there's a very good chance that it was 0%, but maybe you got no lift, but maybe it's between these bounds or something like that. And so not every client wanted answers in this way, but once we thought about it in those terms on the back end, we were then able to make sure that we could give the most accurate information to the clients possible. Another example in terms of understanding probability, which is very common these days, which actually by the time this goes out is going to be driving people crazy, which is all the election predictions. Everybody is talking about every single poll that comes out, and if you read 538 blog or all sorts of things, they always have probabilities coming out about whether one candidate is going to win or another. And that's another case where I think the average person doesn't really interpret that very well. And we have the tools to maybe decipher some of this a little better. One of the things that I like to point out is that this is an example of something called a martingale, which is kind of an interesting vocab term, which just means that, hey, today's prediction has to be the weighted average of tomorrow's prediction. So if you think tomorrow there's a 50-50 chance that one candidate is up 60-40, but there's a equally likely chance that the second candidate is up 60-40, then today's average has to be 50-50. And so that's kind of an interesting way to look at it. And you kind of look at these election predictions and they're not really, they are an example of subjective probability, which I want to talk about, which is how Bayesians often look at probability. Most of us take the subjective point of view, and the subjective point of view is that a probability is something that is calculated by an agent with beliefs. So when you talk about somebody's beliefs, that's a point of view, and we just happen to have not clear beliefs that X is true and Y is false. We also have some probabilistic beliefs where X might have a 10% chance of being true and Y maybe has a 5% chance of being true. And we update those beliefs with new data, and maybe different agents might have different beliefs. Some of them might not be using Bayes' rule at all. They might be using some heuristic, but they're still coming up with beliefs all the same. And we kind of consider that all probability, and we have to kind of decipher who's doing a good job, a good, a competent job at coming up with these probabilities. The hint is if you use Bayes' rule and you use some good common practices with priors and all that, then you're doing a good job. But there's still a lot of nuance in there. You still want to know, am I gathering the right data that I want to gather? Am I looking at the data that I want to look at and all of that? So I think somebody that I interviewed on the local maximum that did a really good job of explaining Bayes' rule that I think was good for the average person that you could catch up on was mathematician Sophie Carr, who I talked to in episode 105. And I really liked her imagery of Bayes' rule being kind of a giant game of guess who, where, as you're gathering more information, you're eliminating some hypotheses and leaving others open. It's kind of a probabilistic guess who. So that's the first one that you should check out. I think that that means that when we take the subjective point of view, we want to take a personal point of view. Or in the case, like when I was doing with Foursquare, with measuring ads, I was saying, hey, I'm going to build a machine here. It's going to have a lot of different parts. It's going to take in data. It's going to update these very complicated probabilistic models. And essentially, I'm going to say, hey, this is going to be our organization's take on where the probabilities lie. And so that's a very subjective way of looking at it, but it's often very helpful when solving problems. Some people maybe are a little bit uncomfortable with the idea of probability as a subjective thing. And so that's something to keep in mind. One thing to keep in mind when you're explaining Bayesian methods, because you kind of have to walk people through that a lot. Like why, I want something to be an objective. I want something to be an objective answer. You kind of have to explain why that might not be, explain why the subjectivity actually works in a lot of different cases. So the other view, as many of you know, is kind of the frequentist point of view. And there are other views as well that I'm going to get into in a second, but this is one that you have to be well versed in if you're going to do Bayesian inference in the real world. One thing to point out is that currently frequentist methods and sort of the objective view of probability is the dominant view of probability taught in schools and universities, both like at the high school level and at the undergrad level, pretty much, well, all throughout the United States, and I'm pretty sure it's very similar throughout the world. So I spoke to a professor about this, Brian Blaise, on the podcast. You go to episode 119, and he wrote a book on Bayesian inference, which was for a younger audience, for an undergrad audience, and turns out that it works very well. Like our method, Bayes' rule, is not that complicated. You could teach that in high school. You could even teach that probably before high school. Okay, maybe not the kind of the calculus version of it, but you could teach the Bayesian way of looking at things very similarly. And yet a lot of the, a lot of university professors and people in academia sort of see Bayes' rule, and I was kind of surprised by this, as like the really advanced math. You've got to kind of work your way up to it, which really, in my opinion, is not the case, and kind of a reason why we as Bayesians sometimes have a little trouble explaining our point of view. So, most of us didn't get Bayes until, advanced courses in statistical inference, or maybe in machine learning. I mean, I personally didn't really have to contend with Bayes' rule until I was in grad school and I was taking courses on data mining and machine learning and that sort of thing. So if you want to know, and if you want to get some more information on frequentist point of view, well, one of the areas in science and life where the frequentist point of view really works is in the area of controlled experiments, because controlled experiments are something that can be repeated over and over again. By the way, the frequentist point of view, I should point out, I kind of assume that you all know what it is, but the view is that probability is kind of a long run value that is sort of the output of experiments. So for example, if you have a weighted coin, you're going to flip coins a lot of times, and you assume that each flip of the coin is independently, is sort of, it is independent and identical. And so you keep flipping that coin, and then eventually the ratio of heads to tails, the ratio of heads to flips, is going to converge onto a number. And that number, after an infinite number of flips, which is impossible, you can't have an infinite number of flips, but that convergence is eventually going to be called the probability. And in experimental design, where you have a very repeatable experiment, that tends to work very well. So I did a whole episode on experimental design. That would be episode 109 with Adam Kapellner. Very interesting stuff there. And so, okay, well, one of the people to look up in experimental design is Ronald Fisher. Very, a lot of work has been done there, but it's from kind of the opposite point of view that a lot of us would prefer to take. Now, another interesting thing, so a lot of this stuff was kind of debated and come up with around the turn of the century. I'm up. Okay, freezing in my own, even though this is not online. Okay, so one of the things that that I came up with, I found a lot of interesting debates and discussions that we're having at that time, maybe around the turn of the centuries, maybe about the 1930s, 40s, 50s. One of the ones that I found very interesting that isn't talked about very much is called the Bernstein-von Mises theorem. And essentially what this, and this is Richard von Mises and Sergey Bernstein, statisticians at Harvard, I think the 1930s. So basically that says that Bayesian methods do tend to converge, even if you and I say start with different priors and we're kind of looking at the same data, or even if, in a lot of modern machine learning examples, we're looking at different data, but it's the same, it's from the same larger data set and we're pulling from it randomly, then we should kind of converge on a similar answer if certain conditions are met. And you should kind of be familiar with those conditions. And one of the, so I did kind of an episode on that. That was episode 77, where I talked a lot about Bayesian thinking and in general, and you should definitely check that one out. But one of the interesting things about this theorem too is if you look at it and you think about it properly, you can kind of look at frequentist methods as having kind of a somewhat of a Bayesian interpretation as well. And so it sort of says that under normal circumstances, which by the way are broken a lot in the real world, so you have to watch out for that, the Bayesian models converge and they converge with the frequentist model, which is kind of a good thing oftentimes, but it does mean that you often have to translate back and forth between somebody who thinks one way and someone who thinks another way. And sometimes you even need to translate back and forth between two Bayesians who are taking a very different approach. So what are the exceptions to this where things can't converge? This is where you can get into trouble. Well, first of all, if you have a different hypothesis space as a Bayesian, all bets are off, because I could not be considered some of your hypotheses and you could maybe not be considering some of my hypotheses. Likewise, if my prior assigns some hypotheses to 0, then that's the same as not considering those hypotheses. And so we're not, if those end up being the right answer, we're never going to converge. Okay, so those might be the obvious ones. Another one that happens is when you have kind of very large and complex priors and distributions. One is when you have kind of an exponential distribution, you have a very fat tail where the data that we're getting can't tell us what happens. Like, there are some very extreme examples that affect the average rate. Like, let's say, I don't know, 99.99999% of the time, I'm going to get a value between 1 and 10, but every once in a while, I get a value that's like billions and billions. That could happen. It actually happens a lot. And so oftentimes with lots of data, even we can't pick up on that. And so that's something to take in mind. Sometimes I've had, issues where, not that particular issue, but I've definitely had issues where, I was running a logistic regression model and one of the variables was distributed exponentially and it was trying to fit kind of a linear weight onto it. That doesn't work too well. So, I mean, one thing you can do is kind of divide it up into buckets and things like that. So another time where this can fail is sort of non-parametric methods. So let's say you want to fit a mixture of distributions to the data, but you have kind of no limit on the number of components, that's often a great thing to do. It's a very flexible way to fit your data, but sometimes this might not hold. So this kind of theorem doesn't hold, and that could be a problem for Bayesian methods, you could say, but it's also a problem for frequentist methods too. So everybody gets in trouble in these situations. So another issue that I discovered when doing all this research for my podcast is that Richard von Mises, who was the statistician, he had this brother, Ludwig von Mises, who was this famous Austrian economist, and he actually had some things to say about probabilities as used in the real world. And it was kind of hard for me to wrap my head around it, because we think one way here in the early 20th century as Bayesians, and they kind of think another way. But I kind of thought that I had to contend with this because it was so interesting. Because he was talking about something called case and class probability. And he sort of warned against treating case probability and class probability the same way. So I sort of knew this has something to do with Bayesian frequentists, is something to do with subjective probability and objective probability, but I wasn't really sure. So fortunately, I was able to get a guest on the program who's an expert in this guy. His name is Bob Murphy, and I got him in episode 107, and we talked about it a little bit. And it turned out that class probability, oh God, I'm going to forget which one is which, but one of them is class probability, where that looks like it's much closer to a controlled experiment where you have one situation that happens over and over and over again. Philosophically, I think that there's also a problem with saying that we're doing the exact same thing over and over again, because we know that's not exactly true. We know that there's always little differences that, but be that as it may, it's, and I think, Laplace talked a lot about this, where we are ignorant enough as to little differences that from our point of view, all of these iterations of the experiment are essentially equal. And so that's kind of one thing to wrap your head around that's pretty interesting. But essentially, when you have these class probabilities, you could really make a good case for coming up with a number. Case probabilities are one-offs. So in the case of one-offs, I think that they didn't really have the tools to talk about one-offs 100 years ago. But today, with the rise of Bayesian methods, we have very good ways of talking about one-offs. And actually, I did an episode on one-offs too. So that would be episode 69. Let me actually pull up here what episode 69 was called. No, it wasn't 69. Shoot, I've got to get a better number for this. I think it was, yes, 65, episode 65, localmaxradio.com/65. You can get them just by typing in the number. So the chance of something that has never happened before. And, this is one of the reasons why Bayesian methods in the middle of the 20th century started to become popular in areas like actuarial science and insurance, because people had no idea how to insure things that were very rare and never occurred before. And Bayesian methods sort of gave them the answer. So that's kind of a good factoid to have up your sleeve. So coming back to the episode that I did with Adam Capellner, because he teaches philosophy of probability in his class in episode 109. And it turns out there are other ways of looking at probability too, aside from subjective and objective, but they're kind of related. So one is sort of propensity theory. So that's the idea that it's sort of an objective inherent way of the world. So for example, if you have a 6-sided die, there is a propensity for each side to come up 1/6, 1/6, 1/6. That's just a property of the die, or property of the dice. Sometimes that's an interesting way to look at these things. This is one that one of the founders of the philosophy of science, Karl Popper, came up with. And it's sort of a mixture between the two, because it's objective probability, like frequentists propose, but it's also one-off. you could do one-off things with propensity theory. So that's more Bayesian. So very interesting kind of mixture there. And then you have kind of the logical view of probability. We're no longer talking about beliefs here, but you have the kind of purely mathematical take on it, where probability is a measure and it has these mathematical properties. And I think that's a great way of looking at it in some circumstances. But you can take your mathematical theory, and I kind of feel like once you have to plug it into the real world, which is science, which is marketing data, which is machine learning, you kind of have to figure out where you stand on objective or subjective. So these issues have, okay, this might sound a little bit like, head in the clouds. People are talking about this stuff in universities. Why do I care? Well, here's a good example of why you should care. One is that the debate between credible intervals versus confidence intervals. And I'm sure you've seen this a lot. The frequentists use confidence intervals. They're way more common. And usually it's a formula, but it's almost always interpreted as a Bayesian credible interval by the public, and not just by the public, but by by clients or bosses or anyone who's looking at this stuff. So Bayesian credible interval is just, hey, I'm going to give you a range of numbers, and I believe there's, say, a 95% chance that the value you're looking for is in that range. And here's the median. Here's the median value, and I think that there's a 50% chance that the number you want is above this range, and there's a 50% chance that the number is below this range. And you could see that's really focused on belief. Hey, it's sort of like, in my expert opinion, I believe that the value has this probability distribution. I think that's often a really powerful way of looking at this stuff. And frankly, I think it's better than the other way of looking at that stuff. But that's just me. But you do have to kind of work on both ways. And the other is kind of the credible interval is kind of more focused on hypothesis testing, which is, we expect results to appear in this range if we had done multiple experiments with our intended answer. So it's sort of harder to wrap your head around. Another one that's very hard to wrap your head around, but it's been very difficult to wean people off is p-values. It's really got the same issue. And it's always worth discussing with colleagues and clients when you're doing these models, is sort of, where do they stand on p-values? What's their opinion of them? Because a p-value says, hey, what is the probability that I am going to get a result at least this extreme given the hypothesis? So you want to know, hey, did my data kind of invalidate the hypothesis? Whereas kind of in the Bayesian point of view, we want to take a look at, hey, we have a range of hypotheses. What's our belief, as represented by a probability distribution over that range, which is often a lot more intuitive. So again, when you're dealing with people who have different views on this topic, you shouldn't try to overturn someone else's way of doing something. That's going to be very difficult. Think about it if somebody was trying to overturn your way of doing something, but you kind of have to be aware of how different people perceive probability. And then you have to translate effectively to and from the Bayesian worldview, or your own worldview on probability, which you should often be thinking about. So I'm going to leave you with one more example from just philosophical thinking. And well, I can't just talk all day about what other people think. I have to talk about an idea that I think is not quite original, but it's sort of my idea on what probabilities are, and it's related to Bayesian inference. Before we close up, because it's sort of important to me. So I did an episode on this, which is episode 108, localmaxradio.com/108, where I tried to answer once and for all not once and for all what is probability, but I gave myself a homework assignment. I said, okay, I'm going to try to give you my take on what is probability in this episode. So I attempted to do it. Spoiler alert, I basically take the subjective point of view, which is common among Bayesians, and I assume common among you too, but if you have a different view, I actually like to hear about it. I also tend to look at probabilities as ratios, which is a little bit different. That probability is kind of a relative property versus an absolute property. So instead of saying, hey, there's a 50% chance that this coin will land on heads, maybe I'm going to say, hey, the probability of X is twice as likely of happening as the probability of Y. And you can kind of translate that from relative to certain. So for example, I want to know the weight of the die. I can say, okay, what is the probability of getting a heads versus the probability of getting a heads or tails? And so then you can kind of see the inherent assumption there that certainty is getting heads or tails, which is a good assumption, but as we know, probably not ironclad 100% true. But interestingly enough, this idea of relative probability, where I can say one event is twice as likely of another without actually knowing what the absolute probabilities are, this works really, really well when it comes to doing Bayesian inference, because when you look at these complex posterior spaces that we use when we apply Markov chain Monte Carlo, and we use pi MC3, and we apply the no U-turn algorithm. This works really well because in those Bayesian posteriors, the denominator of Bayes' rule, the marginal probability, is often dropped, because when you do Markov chain Monte Carlo, each step you want to know if I want to go from this hypothesis and I want to jump to this other hypothesis, and all you care about is the relative probability of each hypothesis. And we don't have the denominators, we don't have the absolute probability of each one. And oftentimes those denominators are not even tractable. So it's great that we can actually have some interpretation of this that is sort of independent of, well, we have this intractable denominator, let's pretend it's there. And so now probabilities often live in a ratio space, which is really interesting. It's not just probability of A, it's often probability of A over probability of B, which means it's a number, it's a positive real number. And so the ratio space is a very interesting symmetry around one, which is a really nice number system to work with, in my opinion. So that's something more to think about. If you have any more ideas on how to take this idea to the next level, I'd be very interested to hear about it. So I think we're running out of time. I hope you learned a couple of things from this. I just want to conclude with a few quick takeaways from my talk. One, okay, I'm going to say this, you can get a lot more information on the Local Maximum podcast, localmaxradio.com. So check that out. I've done a lot of work on that, or reach out to me directly if you have more questions. Two, the philosophical basis for probability is still very much an open discussion. People still think very differently about it, and affects the way that people approach real problems. And it actually comes up, when you're talking to other people in the field, trying to come to a consensus here. Three, you're going to encounter many views on probability, and it's often going to fall to you to explain your point of view and also translate it into other points of view for people you work with, or interpreted it, or to interpret it. So it's your job not just to be a modeler, but to be a teacher as well. And if you get those skills, you can be, that is a very marketable, rare skill in today's world. And four, I just want to conclude with this. I didn't say it directly, but as Bayesians, I just want everyone to know that we have a very, very powerful toolkit at our disposal. And it's taken many years from the foundations of science and trial and error to the rise of machine learning and probabilistic programming like pi MC3 to really build up to this point. And we have special insights into solving problems that many people just don't have. So, don't look down on people who don't have these insights, because it's a very special thing, but you're often going to be the expert in the room on this, and don't forget it. So thank you very much. You can reach out to me, and I look forward to meeting you all in this conference. Take care.